Welcome to this explainer. Have you ever actually stopped to think about how truly remarkable the internet is? We're talking about billions of computers, smartphones, and servers talking to each other every single second across the globe. But here's the secret at the heart of it all. Computers are fundamentally, well, kind of dumb. They have absolutely zero intuition. So how do these unthinking machines manage to have these highly complex, totally error-free global conversations? Well, that's exactly the invisible magic we're going to decode today. Here is our roadmap for today. We're going to cover the language of computers, message anatomy and grammar, ensuring reliable delivery, phone calls versus letters, the 5-layer architecture, and finally, links, routes, and networks. Let's dive right in. Section 1. The language of computers. Imagine trying to coordinate a massively complex project with someone who speaks a completely different language on the exact opposite side of the planet with absolutely zero margin for error. That is literally the challenge our machines face every single millisecond. Because computers aren't intelligent. They can't just use context clues to figure out what someone probably meant. They require incredibly rigid global standards to communicate. These standards are really the unsung heroes of the digital age. They govern absolutely every exchange of messages between hardware or software processes all over the world. Without them, the internet just wouldn't exist. It would just be billions of isolated machines shouting into the void. In the networking world, we call these standards protocols. Now, the absolutely crucial thing to remember here is that a protocol isn't just a polite suggestion. It is a strict rule of engagement. These protocols dictate everything. They decide message order, so literally who gets to talk and when. They dictate the semantics, meaning the exact intent of a message. Like an HTTP request message explicitly means, please give me the specific file, and the response means, here is the file, or I cannot comply. There is simply no room for interpretation. All right, Section 2, Message Anatomy and Grammar. So now that we know computers operate on these strict rules, how do these protocols actually structure the messages they send? Just think about how we communicate every day. Human grammar is incredibly flexible, right? If I jumbled my words or totally misspell a text, you still know what I mean. Computers, not so much. They require absolute structural perfection, which we call message syntax. It's essentially human grammar, but flawlessly rigid. Literally a single bit out of place, and the machine has no idea what you're trying to say. Let's break down this general message organization. Every network message is split into 3 primary parts. You've got the header, the data field, and the trailer. It helps to think of the header and the trailer as a delivery envelope used by the network's switches and routers. The data field? Well, that's the actual letter inside that you want delivered. The header contains crucial delivery instructions, like the destination address. And here's something that brilliantly illustrates how flexible yet strict this system is. Sometimes you don't even need the letter. For instance, TCP supervisory messages, which manage the network itself, are purely headers with no data field content whatsoever. It's literally just an envelope telling the system what to do. Moving on to Section 3, Ensuring Reliable Delivery. So what actually happens when these perfectly packaged messages inevitably get lost in transit? This is where the Transmission Control Protocol, or TCP, comes to the rescue. Let's walk through this process. Step 1. The sender transmits a TCP message, which we call a segment. Step 2. If it arrives in one piece, the receiver sends back an acknowledgement, or an ACK. But here is the real magic in Step 3. If that ACK is never received, the sender just assumes the message was lost or corrupted, and it automatically retransmits the TCP segment. What's really fascinating here is that this creates true reliability. It's not just error detection, where a bad message gets dropped. It requires error correction through retransmission. That is exactly how your downloads arrive perfectly, every single time. Section 4, Phone Calls versus Letters. Much like how we choose between sending a quick text message or making a formal phone call, computers have different styles of digital communication too. Connection-oriented protocols like the TCP we just talked about act exactly like a formal phone call. Both parties have to agree to talk, opening the connection, before a single piece of actual data is sent, and they feature formal closings when they're done. During the exchange, every single message gets a unique sequence number. That way, if there's a gap in those numbers, both sides know immediately that a message was lost. But as you can imagine, this formal handshake comes at a pretty steep processing cost. Let's compare connection-oriented protocols with connectionless ones. Connection-oriented TCP is super reliable, but tracking sequence numbers and managing the connection takes massive overhead. It takes about 7 messages just to open and close a connection. That's a huge burden if you only want to send one tiny piece of data. On the flip side, we have connectionless protocols, like HTTP. HTTP is essentially a fire and forget system. It simply throws the message over the fence without opening a connection or guaranteeing delivery. It's incredibly fast and lightweight, but totally unreliable on its own. Section 5, the 5-layer architecture. Up to this point, we've only looked at individual messages. Let's zoom out and look at the massive corporate hierarchy managing all this digital traffic. Creating a global communication network is staggeringly complex, so engineers needed a broad plan. They did what any smart engineer does. They broke the problem down into smaller, manageable pieces, or layers. We divide the physical hardware functionality all the way at the bottom from the software applications operating at the top. This is a brilliant strategy because it allows specialists to work on one highly specific area without breaking the entire global system. Today, the dominant model running things is the hybrid TCP/OSI architecture. Let's just count quickly up through these core layers. Layer 1 is the physical layer, governing the actual device-to-device electrical connections and cables. Layer 2 is the data link layer, which handles delivering a frame across a single local network. Layer 3 is the internet layer, routing packets globally across multiple networks. Layer 4 is the transport layer, managing the host-to-host communication and fixing errors, just like we saw with TCP. And finally, Layer 5 is the application layer, where your actual apps communicate. Every single layer has a highly specific, totally isolated job to get your data from point A to point B. Section 6, links, routes, and networks. To really grasp how the internet functions, we need to zero in on the most crucial distinction in network engineering, the fundamental difference between Layer 2 and Layer 3. Let's look at Layer 2 first. A data link is the specific path a message, which is actually called a frame at this layer, takes through a single, local switched or wireless network. The data link traces the path from the host computer through the local switches right up to the router. But, and this is key, it completely stops there. A data link handles communication strictly within one network. It cannot cross over into another. Now let's see how this builds into Layer 3, the internet layer. This is where we get the route. A route is a packet's path all the way across the internet, jumping from network to network via routers. And here is a totally mind-blowing fact about network architecture. As your data travels, the Layer 3 packet stays exactly the same from the very beginning to the very end. But the Layer 2 frame that carries it, that frame actually gets destroyed and recreated every single time it passes through a router into a new network. It's like the letter stays safe, but its envelope is swapped out and replaced at every single border crossing. So if you remember nothing else, the crucial takeaway from this explainer is this distinction. The data link layer is your local delivery system. It uses frames and switches to move data locally. The internet layer is your global highway system. It uses packets and routers to carry your data across the world. The entire magic of the internet is really just these two layers working together in perfect harmony, orchestrated by those strict, uncompromising protocols. Which brings us to a final, pretty wild thought. We've seen how fundamentally dumb computers manage to communicate perfectly because they are forced to obey rigid, unthinking rules just to say hello. But as artificial intelligence continues to evolve, what happens to this invisible, highly structured architecture when AI starts writing and negotiating its own dynamic protocols? Will the rigid networking rules of the last 40 years survive, or are we on the brink of a totally new digital language? Definitely something to think about. Thank you so much for joining me on this explainer, and keep questioning how our digital world connects.